Why is it that the 2,000 volts from this microwave oven transformer is actually way more dangerous than the 200,000 volts from this Tesla coil? I can touch the Tesla coil and be perfectly fine, but this microwave oven transformer would almost certainly kill me. Well, the answer is, there's more to it than just the voltage. You've probably heard the saying, it's the amps, not the volts that kill you. While that's technically true, it's not that simple. You can't consider just the one without the other, because they're always related through this little thing that we call Ohm's law. You need enough volts to be able to drive enough amps through your body. 10 milliamps through your heart is generally what's considered to be lethal. That's why I can grab the terminals of this car battery, and not only am I not dead, I don't feel anything. These things can deliver hundreds of amps to crank the engine in your car, but they can't cause anywhere near that amount of current to flow through me because it's only 12 volts and the resistance of my body is very high. Current flowing through me because of this battery is almost nothing. Now, moving on to the microwave oven transformer, we are well within the range of what can kill you. These things put out 2,000 volts, and usually about 1 amp if you short it out, like this. That is absolutely f***ing terrifying. You do not ever want to touch anything like that. That can drive way more than 10 milliamps through your body. So if the Tesla coil puts out 100 times the volts of the microwave oven transformer, then why isn't it 100 times more lethal? The resistance of my body isn't any different. In fact, it may go down due to dielectric breakdown at these kinds of voltages. Ohm's law isn't any different. So what is it then? Well, I'll tell you what it is. There's another resistance, or rather another impedance, this is AC, that we haven't considered. And that's what we call the output impedance, which is the impedance of the voltage source itself. Every real voltage source is non-ideal and has an output impedance. Some are just higher than others. The Tesla coil can create huge voltages, but it can't source very much current because its output impedance is high. That's why I can do this. But I'm not dead. When I touched it, I created a much lower impedance path to ground for the high voltage on the coil. But since the output impedance of the coil is so high, a lot of that voltage actually dropped over the output impedance of the coil itself before it even got to me. So the voltage dropping across me is actually not that high compared to the full voltage that the coil is outputting. Also, a lot of that voltage drops over the arc distance. So by the time it reaches my finger, a lot of it is already dissipated across the arc. If I were to just straight up grab the Tesla coil, we might be having a different conversation. Or no conversation. And back to this thing. Its voltage may be 100 times smaller, but its output impedance is way, way lower. That's why these can source so much more current, and why they are deadly. But Nick, you say, what about the skin effect? I've heard that's why you can touch Tesla coils and not get hurt. Well, I'll admit that's a part of it, but that's far from the most important factor. The skin effect, if you don't know, is a phenomenon where most of the current flowing through a conductor stays near the surface rather than going through the center, especially for AC and high-frequency AC. The higher the frequency, the more the current stays towards the surface and the less of it passes through the center. Here's the thing about the skin effect though. The models we have only apply to uniform, isotropic conducting materials, like metal wires. That is, materials that have the same material property everywhere. Your body is not a uniform isotropic conducting material. Your body is made up of a lot of different materials. Skin, bones, nerves, muscles, blood, all of which have different electrical properties. Electric current is always going to follow the path of least resistance, or least impedance, and there is no guarantee that the skin effect is going to protect you when dealing with a high voltage, high frequency source like a Tesla coil. The skin effect may indeed protect you when you touch a Tesla coil. Sometimes. Under different conditions, it may not. You cannot rely on this to keep you safe. The output impedance is always the more important factor here. Also, if you ever touch really high frequency electrical discharges, like in the megahertz range, you'll probably notice that you don't even feel getting shocked. This has nothing to do with the skin effect. Rather, your nerves can't feel electrical current flowing through you when it changes direction that rapidly. You need to have sustained current flow over a period of time in order for your nerves to recognize that as pain. High frequency electricity could easily kill you and you wouldn't even feel like you're getting shocked. So in the end, it's the combination of the voltage, the impedance of your body, and the output impedance of the voltage source that determines whether an electric shock can be deadly. Experienced high voltage people understand this implicitly and know when it's okay to play around with something and let it shock you, and when you should never, ever put your hands anywhere near something. Anyway, coilers, stay safe, don't electrocute yourself, know your output impedance, and I'll see you all next time.